So I wanted to make a video where we could go through parent functions and talk about them as a topic that is covered in so many courses in high school. And I'm going to do this. It's going to have some stuff that's a little bit more advanced for my pre-cal students, some things for a little bit more basic for Algebra 1 or Algebra 2 students, but I figure this will help everyone. And the first function I want to talk about is a function where you have your x and y axes. And the first thing you notice is that the function itself, f of x, is a horizontal straight line. Now we call this the constant function, and a constant function has the formula f of x equals a number, a constant. And it could be anywhere on the negative side of the y-axis, but the formula y equals a constant tells you it's not changing at all. It's independent of x. No matter which x I put in there, they will always give me the same y value, all these points, and they don't even have to be on specific whole numbers. So if I would put in x equals 0.793 or 2, I would still get back that constant. No matter what my x is, it would give me back that constant. Now, that idea that no matter what my x is, tells you that the domain, the types of x values that can go in this constant function, are negative infinity to infinity. In fact, any number I want to put in for x is irrelevant, and I can put in any number. I can put in irrational numbers like pi. I can put in negative numbers. I can put in positive numbers. I can put in fractional numbers. It doesn't matter. They're all good. I can put in 0 and 1. All the numbers that I could possibly think of can go in here. So my domain is all real numbers. So if you learn domain as that, or if you learn it in set notation, x such that line means such that, x is an element of the real numbers. Any value works here. Now my range or my possible y values are just my constant. So wherever I set my constant function, the range is just the constant that I have. So I'm going to write it as inclusive of that constant. It's just that constant, from that constant to that constant. So if I have f of x equals 5, my range is just going to be 5 to 5. If I can write it as y equals 5, or I could write it in set notation y such that y equals 5, as long as it's equal to whatever my example function is. So this was a relatively silly function in that it doesn't do much. It's a horizontal function. Horizon, it goes across and stays put. It has a slope of 0. Notice that it has a slope of 0, etc. Let's go a little bit more interesting. Let's talk about a linear function. So this is going to be a linear function, linear from line, okay, function. And while we typically think of lines as y equals mx plus b, an even simpler version of a line has a slope of 1 and a y-intercept of 0. So I'm going to do that. I'm going to say f of x equals x. In other words, y equals 1x plus 0, which we simplify to y equals x, and f of x is just a way of expressing y, or the output of a function. For this function, the simplest line is one we could draw right through the origin, right? Our intercept is 0, and our slope is 1. And for this function, I'm going to put my domain. Every possible x value that you can think of can go into a linear function. There are no restrictions. So domain is, I'm going to write this in interval notation because I went over the different notation in the previous example, negative infinity to infinity. And my range is likewise negative infinity to infinity because every possible y value can be represented in this function. And that had our exponent to my x value here was 1, a linear function, x to the first power. Let's head up a degree. Let's go up a power. And let's talk about quadratic functions. Quadratic functions, okay, have the highest degree, the highest power is x squared. So look at the simplest quadratic function as f of x equals x squared, or y equals x squared. Of course, you know that the standard form of quadratic is ax squared plus bx plus c. These can be minus also, but just that coefficient can be minus, that negative, and that constant can be negative. So here I'm just gonna graph our simplest quadratic. If we added some other terms here, we could move it up, down, right, left. We could make it stretch it out and bring it down. And this quadratic, let's talk about domain. Well, any x value can be put in. It's just going to get wider and more and taller depending where we go. So that's negative infinity to infinity. And my range, let's take a look at the range of y values. Well, in my example function here, notice that all my y values start at 0 and they go up from there. So in my parent function, my y values are going to start at 0 and go towards infinity. Now, the reason infinity, by the way, in all these examples has this rounded parenthesis as opposed to a square bracket is because I cannot include infinity as a number. It is a concept. So if I say, oh, go till you hit infinity and then stop, your infinity and my infinity aren't the same. It's not an actual place or an actual number or value, so it's never included because you can go infinity plus 1 or infinity squared or infinity plus infinity. So infinity is a concept. It gets a rounded, non-inclusive bracket. And if I had a different, let's take an example. What if I had put a negative in front of my quadratic and moved it down 3? So what if my actual function is y equals negative x squared minus 3? So in this case, if you graph it, you can see, or if you know your translations of functions, you would see that my range here, my domain would still be negative infinity to infinity, but my range would be negative 3 and below. So I'd start at negative infinity and go until negative 3 inclusive.